Okay, so what we're going to do is I'm going to show you how to solve a relative velocity problem, okay? So let me just kind of read the problem and I'll draw it out as I'm doing that. So first of all, we're talking about a soccer game, and we have an individual named Juan, and Juan is running up the field north. So he's running north up this field. So what I want to do is I'm gonna like draw a vector as I'm describing what's happening. So Juan is going straight north up the field, and he is running at 8 meters per second. Okay. Now this is Juan's, and I'm gonna abbreviate Juan with just, so Juan is Juan, of course, and I'm just gonna abbreviate it with a J. So I'm gonna say this is the velocity of Juan, J, relative to the Earth. So this is a relative velocity question. So, all right, so he's going due north 8 meters per second. Great. Now what happens is one of his teammates kicks the ball to him. So there's a ball being kicked to him, and the ball being kicked is at 37 degrees east of north, and it's being kicked at 12 meters per second. Okay. So what I might want to do is construct like a little axes like that, and put this down here like this. Now, what I said was the ball is going 37 degrees east of north. So what you want to do is go north. First of all, you go north, and then you go east. So when someone says east of north, what that means is north is the primary axis, and then you go east from there. And so it's 37 degrees. So it's 37 degrees, and you can see that's east of the north. So we go north and then we go east, right? And so this is also 12 meters. This is 12 meters per second. 12 meters per second. Now this is the velocity of the ball, because someone just kicked the ball, relative to the Earth. Now that's great. Now what I want to know is I want to know what is the velocity of the ball relative to Juan. Okay, that's the question I want to know. All right, so in order to do this, so I have three vectors, right? I have the velocity of Juan relative to the Earth, velocity of the ball relative to the Earth, and then velocity of the ball relative to Juan. So how are you going to, so basically you want to say some vector is equal to the two other vectors. And so how are you going to do that? Well, this is what you should do, is look for the intersection. So what I want to do is look for, in the velocities here, look for where the numerator is the same and the denominator is the same. So for the numerator, so we'll go, looks like B and B. So those are the same values for the numerator in the relative velocity vector. And then that's the numerator. And then for the denominator, we're looking for things that are similar. So E and E. And so you can see here what vector is common among all three. Well, it's the center vector, right? It's the velocity of the ball relative to Earth, okay? So that's what you want to do. So that's how you're going to set up your equation. So now that I know that, I can say the velocity of the ball relative to Earth, which is that middle one there, is equal to just the other two vectors. Now you can write them any way you want to. You could put J slash E or V B slash J. It doesn't really matter how you add vectors. A plus B vector is the same as B plus A. So anyway, so let's do the velocity of, let's say, the ball versus Juan, relative to Juan, plus the velocity of Juan relative to the Earth. Now, what actually is going to happen here is how you could think about this is once you're done, you could think of, because this J and this J like canceling out, and then you end up with V B over E, which is actually what you have over here. So you can kind of think of it like that. Like how does this actually work? So VB slash J, or the velocity of the ball relative to 1 plus the velocity of 1 relative to Earth. You could think of it as the J's canceling out, and then it just leaves the B on top in the numerator, and then the E on the bottom in the denominator, and yeah, and that's just how it works. Okay, so once I have this, the next thing I want to do is maybe sketch out kind of like what these vectors look like. So the thing that you need to be aware of is that the main vector, the velocity of the ball relative to Earth, that's the main vector. So what I want to do is I want to maybe draw that one first. So I'm going to draw like this, draw an axis like that. Okay. And remember, this one looks something like that. And remember, it's 37 degrees right there. Okay, and so that of course is V, the velocity of the ball relative to Earth. Now, I have two other vectors, but I don't like the velocity of the ball relative to 1. I don't know what that looks like. But I do have the other one. Now here's the thing about this vector, and I'll end up erasing this thing, but the vector looks like this. Now, basically, this vector has to, because this, and I'll end up erasing this in just a second, but this vector here, I need to take two vectors that add up to this thing. So I need to somehow take, do something like this plus this, or whatever, or this plus this. But basically, I have to take two vectors that have to add up to that black one, right? So it doesn't even matter. You can go like this way and this way. It doesn't matter. But the point is that out of the two remaining vectors, one of the vectors has to share the tail with we'll call it the main vector, and then one vector's head has to share the head of the main vector. So yeah, so just kind of remember that. All right. So basically, they have to touch it, right? The two vectors have to touch the main vector. All right. So let me just go back in time a little bit. So because I have this black one and it goes straight up the velocity of 1 relative to Earth. Well, what does that look like? Well, it probably is like right here, right? It probably goes up something like this, right? Because it does go straight up, and so that's probably it. So the velocity of 1 relative to the Earth looks like that. Okay. And so if that's true, that means the vector that we're looking for, or the velocity of the ball relative to 1, is probably this guy right there on top, the velocity of the ball relative to 1. Okay, so this is sort of a sketch of what our vectors probably look like. Okay, now so what I want to do is I want to like analytically figure out what does the velocity of the ball relative to 1. What does it actually look like? Like what are its actual what's the actual velocity in meters per second, and then where is it? Okay. So let's do that. So I have this equation, the velocity of, so this equation right, hold on. So this equation right here, but I want to actually look for V, the velocity of the ball relative to 1. So where is that at? So that's this one. That's this one. I'm looking for that. So I need to like rearrange this equation, right? So I could rearrange it as the velocity of the ball relative to 1 is equal to the velocity of the ball relative to Earth minus the velocity of 1 relative to the Earth. Okay, let me take that away. Oh, sorry, to the earth. Great. And so now let's just do that. So the velocity of the ball relative to the earth. Do I have that? Well, that one is that's this middle vector up here. It's a little tricky because it's 37 degrees, 12 meters per second. So I don't know the actual I don't actually know the component values of it, so we'll skip that one for right now. But it is some vector here, right? Minus some other vector. Now the velocity of 1 relative to Earth, that's the straight up one. That's the vector that goes straight up, and it's 8 meters per second straight up. So its x coordinate is 0 because it's not moving in the x direction, and its y is 8 meters per second straight up. So I know that vector's components, but the other vector I don't know. And so how are we going to figure that out? Well, using trigonometry. So I'm just going to draw this right here. I'm going to put this here, and I'm going to go 37 degrees. All right, this is the vector. And then this vector has components, right? So it has this side, and this side. And so these are the components of this vector, right? This vector right here, which is 12 meters per second. Okay. So how do I get the up and down, right? For example, or the vertical? Well, that's just 12 meters per second times, and then 37 is on the inside, so that's the angle. And then I want what is adjacent next to it. And so adjacent, of course, is cosine. And so I'm going to do 12 times the cosine of 37 degrees. And so that should be the vertical velocity. And on top, the thing that's going left and right, or the horizontal velocity, should be, because it's opposite of 37, it is 12, which is the total speed, times the sine of 37 degrees, okay? Now, if you do that, you'll end up with 7.22 meters per second in the horizontal direction, and 9.58 meters per second vertically. Great. So now that I know that, I can put these in my vector down here. I can say 7.22 in x and 9.58. 9.58. Okay? Great. And so now all I have to do is subtract these two vectors. So I have to subtract, let's just do this. I have to subtract this from this, and I have to subtract this from this, okay? So, and then I'll end up with a vector. So 7.22 minus 0 is 7.22, and 9.58 minus 8 is 1.58. Okay, so now I know this vector, the velocity of the ball relative to 1, I know its coordinate components, but I don't know like its actual angle, like where is it, and I don't know how fast it is, okay, or I don't know its velocity. Great, so let's figure that out. So in order to do velocity, we're going to use the Pythagorean theorem, right? And so we're just going to say equals square root of 7.22 squared plus 1.58 squared, right? And we're going to do all that magic, and that's going to come up with 7.39 meters per second. So this is how fast the ball is moving relative to Juan. Remember, Juan is running north. He's running straight up the field at 8 meters per second. So relative to him, as he's like looking at the ball and as he's running, he thinks, remember, because the ball was actually kicked. Someone kicked the ball at 12 meters per second, right? Relative to the earth. But relative to Juan, it's not 12. It's actually 7.39 meters per second, right? The next thing I want to know is, what is the angle? What is the angle of this ball? Okay, so what we can do is we can draw another kind of grid like this, and the ball is, well, I need its coordinates, and its coordinates are right here, 7.22, 1.58. So it's 7.22 in x, something like that, 1.58 in y, something like that. So the vector looks a little bit like that. Great. And so what I want to do is I want to put an angle here. We'll call it phi. And yeah, so I want to break this up into the horizontal component. Oh, well, I actually already have a horizontal component. And the vertical one. Great. So the horizontal component is, how long is this horizontally? Well, we know that what that is 7.22 and meters per second, and we know the vertical component is 1.58. Great. And so what I want to know is phi. And so what trigonometric function should I use if for phi if I know the opposite and the adjacent? Well, that's tangent, of course. So I could say the tangent of phi is equal to opposite. I'll just write this down, over adjacent. And the opposite here of the phi is 1.58. And the adjacent is 7.22. Okay. Now, the problem with this is I'm looking for the angle I'm actually looking for phi. And so what I want to do is I want to do the tangent inverse. So I'm going to say tangent inverse of tangent of phi equals the tangent. I have to do the tangent inverse on both sides because it's an equation of 1.58 over 7.22. And what this does is this tangent inverse actually gets rid of the tangent that like undoes it, and then you just end up with phi of the tangent inverse of 1.58 over 7.22, and you can just like plug that into your calculator, and you'll get 12.34 degrees. Okay. And so where does that go? So that's this. So what we just created was this vector here. That one. That's one that we were looking for. And so to recap, that vector there is the velocity of the ball relative to Juan. Remember, the ball was kicked at 12 meters per second. Juan was running at 8 meters per second straight north. But the ball relative to Juan is actually running at, or moving at, 7.39. So that's this, 7.39 meters per second, and 12.34 degrees. So you can see that right there, right here. So it's like 12.34 degrees north of east. So you're mostly going east, and then you go north a little bit. And how far north are you going? Well, 12.34 degrees. So you could, if you wanted to, like a little line here if you wanted, and put like phi here, where that phi is 12.34 degrees. So yeah, so the length of that arrow, its velocity, once again, is 7.39 meters per second at 12.34 degrees. So anyway, this was just a simple little tutorial on how you can solve a relative velocity problem. Once again, what you do, you kind of write down your vectors. You write down what is the common one and call that one like the main one. And then you write the equation down with the main one first is equal to the sum of the other ones. And then you kind of just draw a sketch. And remember, when you draw a sketch, you draw the main one first. And then remember, when you're drawing the other two, one of the other two's tails will touch the main tail. And then the other one's head will touch the main's head. So just remember that when drawing it. And then after that, all you have to do is just basic vector math and then some trigonometry. So anyway, that's it. Hopefully that was useful.